today. So now we have the third lecture of Jean-Pierre Desmailly, and the title is L2 extension theorem and application to algebraic geometry. Thank you very much, Jean-Pierre, and have a nice talk. Thank you.
Okay, thank you, Marco, and thank you to all organizers and to the CIRM and the ICTP for giving me the opportunity to give this series of lectures. So good morning to everyone. So today I will concentrate on applications. So I hope it will be a slightly less technical and with more applications to algebraic geometry. So let me introduce a few more concepts. So first, the analytic definition of log canonical thresholds, which are of course very meaningful for divisors on projective varieties. But here we can define them in the context of plurisobharmonic functions. So you take a domain in Cn, so the things will be local, in fact, f a holomorphic function, and phi a plurisobharmonic function on the domain. Then given a point z0 in the domain, you define the log canonical threshold c z0 of phi. It will be a strictly positive number, but possibly plus infinity. It's also called the complex singularity exponent. And it's defined to be the supremum of all positive numbers, such that exponential minus 2c phi is L1, locally L1, on a neighborhood, arbitrary small neighborhood of a given point z0. And this number measures the singularity of phi. Of course, if phi is smooth, then any number c works, and then you get plus infinity. But if phi has a lot of singularities, then you have constraints. And for instance, a well-known theorem of Skoda asserts that the inverse of this number, c0 phi minus 1, is comprised between the Lelong number, nu phi z0, and 1 over n times the Lelong number. But let me give you a proof because it's very simple. So suppose alpha is a Lelong number. And then this means that phi at z decays faster, it goes to the negative side, it decays faster than alpha times log of c minus z0 plus constant. Therefore, if you compute exponential minus c phi of z, 2c, you get something that is larger than 1, well, constant, over z minus z0 raised to the power 2c alpha. But then, of course, this 2c alpha, if it is larger than 2n, so if 2c alpha is larger than 2n, then you get something that is plus infinity. So you are not in this range, and therefore this proves that the supremum, the sup now, this implies that the sup will be less than n over alpha. Okay, and this gives the lower bound. The upper bound is much more subtle, and actually, well, not prove. It was proved by Skoda at the end of the 60s. Well, you can prove it using the Ozawa-Takigoshi and reducing it to holomorphic functions. But well, it's a well-known result, so I will not prove it here. Okay, now more generally, given the holomorphic function f, you can introduce the weighted log canonical threshold. So you do the same, but instead of integrating the function 1 here, you integrate the square of the function f. And you wonder when this is L1, which means that f belongs to some multiplier ideal sheaf of a multiple of phi. Okay, and now I come to a very fundamental result that was obtained by Guan and Zhou in 2013. Here I'm stating a slightly improved version due to Pham Hoang Yep the next year. So again, you take a holomorphic function on an open set omega by a Parisi-harmonic function. Then you have the following semi-continuity theorem. Assume that on some relatively, so you have your omega here, and then you take omega prime, which is relatively compact. And then you will take an even smaller set omega double prime, which is again relatively compact omega prime. So assume, to avoid boundary issues, that the integral over omega prime of exponential minus 2c phi converges with respect to Lebesgue measure. And then there exists a number delta positive, such that if you have another function psi on omega prime, harmonic, that is close to phi in L1 norm, so the difference of psi minus phi in L1 norm is less than delta, then it will have the same convergence property at any point in omega prime, or at least, yeah. But even with larger numbers, so you can even slightly increase this. And moreover, the exponential of minus 2c psi will converge to exponential minus 2c phi in L1 norm on any relatively compact open subset omega double prime. So it's very strong because, of course, when you take an exponential of a negative function, you enormously increase the size. In spite of just having L1 convergence, which, by the way, is the same as weak convergence in the sense of distributions, then you get this very strong convergence in L1 norm of the exponentials. Okay, and from this you derive what was called the strong openness conjecture, so strong effective openness. Now, if you approximate from below, so you take Parisi-harmonic functions that are less than phi, and you assume that they converge in L1 norm, again by shrinking to a relatively compact open subset. Then, even with the weight, then f square exponential minus 2c psi converges to f square exponential minus 2c phi in L1 norm, provided with respect to this weight function, you had convergence to start with. Okay, as a corollary, well, this log canonical threshold actually is reached as a supremum, and when you take the upper bound, then you get an open interval actually. So when you take the sup, actually for the sup value, you have non-convergent interval. Okay, so it's an open condition to be integral. So that was a long-standing conjecture, but finally, as you will see, there is a relatively simple proof by the Ozawa-Takegoshi theorem. Okay, and of course, well, this corollary is a rather easy consequence of the previous theorem. In that case, you simply take psi, you can assume phi negative, of course, because you subtract the constant. And then you take psi to be 1 plus delta phi, so it will be less than phi, so you are below, and you apply the previous convergence theorem. So it's just a special case when psi is a multiple of phi. And as an application to multiple ideal sheaves, you get the fact that the upper semi-continuous regularization of a multiple ideal sheaf, so it means you take I plus of H, it means that you slightly increase the singularities by raising to power 1 plus epsilon. So the weight is multiplied by 1 plus epsilon. But in spite, so it's the same, of course, as taking a discrete sequence, 1 plus 1 over k. When you do this, you get an increasing sequence of coherent ideals. So by Noetherianity, you know it has to be stationary. But a priori, this stationary limit could be different from I of H. But in fact, the Guangzhou results tells you that this increasing stationary sequence converges to I of H. Okay. And also, in terms of the log canonical thresholds, of course, if you have psi which is less than phi, so it means more singular, it's more negative, then the log canonical threshold is smaller. But if psi converges weakly to phi, then you know that the log canonical threshold will converge. So you have a very strong convergence results for log canonical thresholds. And of course, it contains similar results for the log canonical thresholds of sections of line bundles, of divisors, and so on. So again, this is a direct consequence of the second part of the main statement by Pham. Okay, so now I'm going to tell you a few ideas how to prove Pham's version of the Guangzhou theorem. So actually, you prove it by induction on dimension. Well, in case n is 0, this is completely trivial because holomorphic function is just a constant. So you are just saying that, well, there's nothing to prove in that case. It's trivial. For dimension 1, it's also not so hard because you can characterize. So in dimension 1, you know that integral of exponential minus 2 phi is locally convergent at a point. On the neighborhood of the point, if and only if the Lelong number is less than 1. And this is, of course, an open condition. So dimension 1 is easy because in that case, you don't have this Skoda range between factor 1 and n, but n is 1. So you have equality, and therefore you derive it directly from theory of Lelong numbers. Okay, so now we proceed by induction. So assume that you are done in dimension n minus 1. Okay, and then you assume that the integral with respect to f of exponential minus 2c phi dv 2n of z converges, and you would like to show that you can slightly increase c to still get convergence. You want to apply induction. So the idea is you are going to restrict to a hyperplane. And in fact, you are going to take a generic hyperplane. So for instance, you choose the last coordinate, and then you will take Zn equal to Wn with Wn very small, but in some set positive measure, and generically in some sense. Okay, but then if you restrict to a hyperplane, if you assume the result known by induction, then for the restriction, you can increase the coefficient because it's the induction hypothesis. And now by Osawa-Takegoshi, you are going to extend the restriction to a function. Okay, so maybe I draw a picture. Okay, so you have your n-dimensional polydisk here with the coordinate axis. So here you have the last one, and here you have the other one, so n minus 1, so this is in Cn minus 1. Okay, and now you have your function f here. which takes values in C, which is holomorphic. And then, well, you restrict it to a hyperplane here. So you take the restriction to the hyperplane Zn equal Wn. And of course, because of Fubini, you apply Fubini almost everywhere on this intersection in n-1 variables. So in the C, well, in the intersection Zn equal to Wn, intersection with the polydisk, this thing will be integrable almost everywhere. Okay, but now you are in dimension n-1, so you can increase the coefficient. And now, after you increase the coefficient, you can apply the Ozawa-Takeuchi to get another function that is now integrable with respect to this larger coefficient in dimension n. Okay, so let me write it. Okay, so here you have your initial function on the polydisk of poly radius R. But now we are going to also prove the semi-continuity at the same time. So assume at the same time that you have a sequence psi j converging to phi, and if the function is not identically 1, you assume that you are from below. Okay, well, just think that you are from below. Okay. Then, by what I said, you can restrict to the hyperplane and then extend again for each of the functions psi j, because you know that for psi j, after you restrict, you can apply the full force of the semi-continuity. So you know you have convergence of the integrals in dimension n-1. You know you can increase C. So you can find a C twiddle, which of course may depend on the choice of the hyperplane. So it may depend on the Wn. And you can find Fj for each of the weights satisfying the integral. And in fact, just by counting areas, you can achieve this bound just by Ozawa-Takeuchi. And moreover, if you look, you can divide now, because you know that the functions, the original function and the new function Fj of z coincide on Zn equal Wn. Therefore, the difference is divisible by Zn minus Wn, and therefore you get a holomorphic quotient. Now, you look at the Taylor expansion at 0, and you look at the lowest monomial that appears in the sense of lexicographic order. So this is the same as in the theory of Gröbner polynomials. Okay, so you take the initial polynomial. In fact, by just a very simple argument, looking at the power series, you can conclude that you can always take in lexicographic order the initial monomial of Fj to be less than the initial monomial of F. Okay. Now you have, well, you have this bounds. Okay. So I explained all this already. And then, well, you apply simply the mean value inequality while you have to carefully select the radii. So in fact, well, you have to, again, to shrink several times. Of course, by compactness, you don't know exactly what happened with the boundary. So you're going to take a large radius and then some intermediate rho and then a smaller radius r, okay? And by applying the mean value inequality, you derive from the integral bound, you derive a sup norm bound. This gives you precisely what you need in terms of the initial monomial, because you have the control on the vanishing and the size And so you derive a bound, and you derive also the this fact. But now, of course, you use some noetherianity argument. So you can somehow iterate the argument. So you get a function in n variable, which is integrable with respect to a larger coefficient. And at the same time, you control the initial monomial, but by noetherianity, if you look at the full ideal, it will be generated by finitely many monomials, terms with given monomials, and then by a careful Gröbner basis argument and division argument, you can prove that your original function, in fact, your original f, belongs to the ideal that is generated by your fj. But now your fj are integrable with respect to the larger coefficient, and you're done. So this is the core of Phams' proof. So it's very, very clever, but in the end, not so long. It's like 2 pages or something. Relies, of course, essentially in the fact that you have uniform constants in the Ozawa-Takiguchi theorem. Okay, so now I'm done with this, and I'm going to really enter into applications to algebraic geometry. Okay, so let me first recall some concepts about the volume and numerical dimension of currents. So you take x omega to be a compact Taylor manifold, and T a closed positive 1-1 current on X. Then Sébastien Buxom has introduced his PhD thesis, positive intersections of currents. So you have here a cohomology class of type PP, which corresponds to some sort of positive intersection of the current. So it's represented by a positive current of type PP closed. And here is the definition. So remember that during the second lecture, I suppose, I proved the approximate Zariski decomposition. So it depends also on the Bergman approximations, which themselves are based on the Ozawa-Takiguchi. So you have currents that are approximations. So you add epsilon omega to make it a Keller current strictly positive. Then, of course, you lose a little bit when you approximate, but you're still positive. And then you have approximations Tm epsilon with analytic singularities. You blow up so as to replace the singularities by divisorial singularities. And after you blow up, now you get a divisor plus something that is left, which is a Keller form upstairs on the blow up. Okay, so now you take this Keller form, you raise it to power p, and then you take direct image to come back to X. Okay, so you have the Keller form here upstairs. You take the power, and then you push forward. So you get now a current that, of course, depends on M and epsilon. But it turns out that there is essentially a unique cohomology class that you obtain. The current is not unique, but the cohomology class is completely unique. And that's called the positive intersection. Especially the volume is the top intersection in this sense. Okay, now you can introduce the numerical dimension of a current. It's by definition the maximum of the exponents P such that this P intersection is non-zero in the HPP. And since you can do this for arbitrary currents, in particular, if you have a Hermitian line bundle, which is assumed to be pseudo-effective, of course, I didn't write it. So you assume it to be pseudo-effective here. So you assume that the curvature is non-negative. So you have a current which has an integral class. And you can use this definition to the current to define the numerical dimension of LH to be the numerical dimension of the curvature current. Okay, and this now allows to obtain a generalized version of the Nadel vanishing theorem. Okay, so you take X to be compact scalar. Of course, it's also true for projective. And LH, a pseudo-effective line bundle with a singular Hermitian metric H. And of course, you assume that, again, I didn't write it, but you assume that theta LH is a semi-positive current. Okay, now you have this concept of numerical dimension, which is the top intersection product that is the maximum of the P such that the piece product is non-zero. Then the cohomology, Q's cohomology of X into the canonical bundle Kx, tensor L, tensor the upper regularized ideal sheaf is 0 for Q larger than N minus the numerical dimension plus 1. So of course, the big case, so if the bundle is big, so it means that, well, it's not completely trivial, it's equivalent, but can be shown. So results with Perron obtained long ago. So this shows that this is equivalent to numerical dimension being equal to n equal dimension of X. So of course, in that case, this number is 1, and then you get vanishing of cohomology. If you have strict positivity, you get vanishing of cohomology starting from degree 1. So it's definitely a generalization of the more usual Nadel vanishing theorem. And that was the point when Junyan Cao obtained his PhD thesis in 2012. But shortly afterwards, of course, Guan and Zhou showed, I gave the argument here, that I plus of H is equal to I of H. So actually, you can remove the plus here, and you conclude that it's true for the original multiplied yield sheaf, which is, of course, much better. Several remarks here. So you also have a concept of numerical dimension of a class. And in that case, you can define the numerical dimension of L to be the maximum of P such that the positive intersection product of C1 of L is non-zero. But here in this definition, it's a little bit subtle, because to compute this, you allow approximations which are slightly negative. Okay, so you allow currents which are slightly negative. You add back epsilon omega to make it positive. You raise to power P and observe that when epsilon goes to 0 anyway, this epsilon will cancel by the Keller condition. And you look at the maximum of P so that in the limit you get something non-zero. So you get another value, which of course is always larger than the numerical dimension of LH, because you can always take the L, the H that you have at hand. And in fact, the supremum for all those which are positive is less, but can be strictly less. So here it can be. There are examples where if you restrict to currents that are semi-positive, you get a supremum that is strictly less than the supremum you get by allowing slightly negative currents. So in that sense, this number is still a little bit weaker than the numerical dimension of L. But of course, the result is probably wrong if you replace, is wrong certainly if you replace by numerical dimension of L. Well, in the projective case, there are some sense purely algebraic proofs of this. In fact, GMA 2G gave also another more algebraic definition of the numerical dimension, although it still uses the multiple ideal sheaves. But of course, in the case where you have algebraic singularities, you can define algebraically the multiple ideal sheaf. Okay, so what's the algebraic definition? So you take holomorphic sections, you count the number of sections on any p-dimensional subvariety for L tensor M twisted by multiple ideal sheaf restricted to, well, it should be Y here. And you look at the maximal dimension of the subvarieties for which this grows at maximum speed. And this dimension now can be shown to be the same as this more analytic definition. The proof uses, of course, a lot of arguments, for instance, the Homander's estimates and so on, to derive the existence of sections from the positivity assumptions. Okay, in the projective case, there is a simpler proof by the standard hyperplane section argument. So in fact, you take A to be very ample, take the associated Kähler metric, omega curvature of A, and then take a complete intersection Y of n minus P members. So you get something p-dimensional. And then you look at the numerical evaluation of this piece intersection product on Y. And of course, the cohomology class of Y is just omega to the n minus P. And therefore, this thing is strictly positive. But then it just means, well, you can show this. It means that if you restrict to a generic Y, like this, the restriction of theta LH has strictly positive top degree, and therefore is big. And then, well, you can show, well, this uses a Riemann-Roch argument, that there exists a metric, because you have a big bundle, so you have the Kodály lemma that you can decompose as a sum of ample plus an effective divisor. Any big divisor, the sum of ample plus effective. And using this, you construct a metric, and you can show that you obtain the I plus of H. This is because of the approximations. That is strictly positive because you have an ample part. Okay, so you have an ample part, so you can get it to be strictly positive. And then you apply the nadal on Y. You apply the nadal on Y, but then because it's a complete intersection, then a standard exact sequence argument reduces the cohomology on X to the cohomology on the hyperplane section. So you go down to Y, and then you conclude from vanishing on Y that you have vanishing on X. But of course, this works only for degrees large enough. So it's a standard induction on dimension by a hyperplane section argument. Okay, so now I'm going to give the more involved proof in the Kähler case. Well, in all these theorems, you're very much interested in having theorems that are valid without any strict positivity assumption. And you even want them to be true in the Kähler case or with foliations, or, okay, you absolutely want to avoid any strict positivity assumption. And this would be crucial to, for instance, extend the minimal model program to case of arbitrary projective manifolds, because then you don't have any strict positivity of Kx. Okay, so all these sort of things, the difficulty in the Kähler cases is very related also to the fact that you don't have strict positivity. So in some sense, if you succeed to get such a general proof, you are in a better position now to attack some of the unsolved conjectures. Okay, so you first apply the regularization theorem. So you start with an LH, okay, which is possibly extremely singular with very, very bad singularities, but at least you know it's a positive current. Okay, then by you use the Ozawa takegoji, of course, here, the L2 extension theorem, you get a regularization H twiddle epsilon with respect to a smooth reference metric H0 given by a weight exponential minus phi epsilon twiddle with analytic singularities, but then you lose a little bit of positivity. So you have, say, a lower bound minus 1/2 epsilon omega here. Okay. But then you have analytic singularities, so you can blow up to achieve now divisorial singularities for this metric. And now, when you blow up, you can remove the divisor of poles, and then you get a smooth metric, even a Kähler metric. And then you can apply Yau's theorem to solve a Monge-Ampère equation that is non-singular upstairs. But now if you view it downstairs, it can be viewed as a singular Monge-Ampère equation downstairs. And then you get a slight modification of this by forcing the volume to be, the density of volume to be a constant. Okay, so you have this Monge-Ampère equation, theta LH epsilon plus epsilon omega to the n is a constant, C epsilon times the volume form omega. And then you count what is the constant. Well, so you compute the volume of this, but it's given by the Bookson approximation of the intersection product, because you remove the divisor of poles. But then you assume that you have a numerical dimension p, so you have this contribution of the piece part, which gives you that, well, this constant goes to 0, but not faster than epsilon to the n minus p. Okay, it's just because of the assumption by the binomial formula and the assumption on the numerical dimension. And another important fact, which I will not really prove here, is that you can track the singularities, track the modification by Yau, but the modification by Yau is only by a smooth factor upstairs. So it doesn't change much the sheaf upstairs. And then you actually get that the I plus of h, which is equal by noetherianity to I of h1 plus epsilon for some epsilon, can be taken to be equal to I of h epsilon. And in the end, by Guan and Zhou, this will be the same as I of h. Okay. And now one uses an argument that was used by Christophe Murugan, again, in his PhD thesis in 1996. So you look at the eigenvalues, so it should be h epsilon here, of the approximating metric with respect to omega. So you have at each point, of course, they are depending on the point, there are functions, but the product of the eigenvalues by this condition is a constant C epsilon, so it's essentially a constant times epsilon to the n minus p. There are n terms, and the product is epsilon to the n minus p. So not all of them are as small as epsilon. Okay, so in fact, if you so it implies that at least some of the lambda j will be larger than constant epsilon to the n minus p over n, which is 1 minus p over n. So it decays, it's much larger than epsilon, some of them at least. Okay, but you don't know, because some of them can be very large and some of them very small. So you have to argue on the relative size of these. So now the next next idea is that you compute the n minus q power with h epsilon again. And then this gives you something that is, well, at least larger than the product of the largest eigenvalues. Okay, so it's larger than the product of the order of your eigenvalues, like this. So you take the n minus q largest, and the integral is bounded by a constant, because this is a Chern class. And therefore, on a very large open set, they cannot be too large because the integral is bounded. So you use a Lebesgue argument, and therefore, you know that the product is this size, and you know that the top ones are not too large. Therefore, you conclude there is a very large open set on which the q smallest are still have a reasonable product, and therefore it gives you an even better bound that the lambda q now is larger than c epsilon n minus p over q. And now you use the Bochner formula. But in the Bochner formula, you need this sum, the sum of the q smallest. Remember that you have to subtract epsilon because you added epsilon. Here I forgot it should be plus epsilon omega. Here, so okay. But then you have to remove the epsilon. But anyway, this lambda q is much larger. So removing something now does not affect this, which is larger. And therefore, you get a strictly positive sum on a very large open set. Okay, now you apply the Bochner-Kodaira formula for this approximating metrics. And then you're almost okay because you know that this constant is strictly positive and bounded below, actually, on a very large open set. So you still have to argue on the volume of the set where it doesn't work. But because of a volume argument, then you can go to the limit as epsilon to 0, and you conclude that your u has to be 0, and you have the vanishing. Okay, so it's rather involved, but still doable. Okay, so now I guess I still have a couple of minutes. I'm going to explain another related theorem with pseudo-effective coefficients, again, without any strict positivity assumption. So just positive current here. And then I'm looking at the Lefschetz map. So, you know, for the Hodge groups, if you multiply by the Kähler metric to some power, then it gives you an isomorphism of groups in the Hodge diamond that are completely symmetric. Okay, but here they are with values in the line bundle tensored by the multiplier ideal sheaf. Okay, instead of being with coefficient c. So instead of c. Of course, if you take the trivial bundle here, it's well known that it's an isomorphism and you don't have the multiplier ideal sheaf. But now, if you have a line bundle and its multiplier ideal sheaf, the statement is that you still get a surjective morphism. And this I obtained, more than 20 years ago with Peternel and Schneider. Actually, we started this paper with Schneider even a few years before. He died actually in 97. And the proof is based on using approximated metrics. So again, you approximate your h by a sequence, h nu equal h0 exponential minus phi nu converging to the phi that defines h. And you can always achieve that they have singularities only on some analytic set z nu, which may possibly increase. And you lose a little bit of positivity, but the epsilon nu goes to 0. Okay. And then you take Kähler metrics omega nu that decay to omega, but are complete on x minus z. It's well known also, it's observation of Grawert, but also used again in the 80s. You have complete metrics on the complement. Now you use some sort of Buchner formula again. You take a cohomology class U. You have these approximating metrics omega nu, h nu. You take a harmonic representative U nu with respect to these metrics. And then pointwise, you have the Lefschetz isomorphism. So pointwise, you can divide by the omega nu to the q, and you get a form V nu, which is of pi degree n minus q 0. And then you have this Buchner type formula that gives you the relation between del bar and del bar star of U and the del bar of V and the curvature. This is the exact formula. Of course, if you plug here the harmonic representative, this will be 0 now. If you take U equal U nu, so you have 0 here. If this would be positive, then you have two positive terms, and you conclude that del bar V is 0, and you get your cohomology class, and you get the surjectivity. Unfortunately, it's not semi-positive. You have a small error, so it's slightly negative. But then you conclude that it's small. It's not 0, but it's bounded by the curvature that you have, which is q times epsilon nu times this integral of u nu. But because u nu is harmonic, it's less than any representative u. So you have this obvious lower bound by going from any representative u to the harmonic one. But then the phi nu decays to phi, the phi nu decays to phi. So you have this bound in terms of the original integral, which is finite. And therefore, as nu goes to infinity, it converges to 0. Still, there is a requirement. Here you conclude that the integrability is with respect to exponential minus phi nu, which is not necessarily the original multiple ideal sheaf. So if you want to prove the theorem, you have to be able to approximate by keeping the same multiple ideal sheaf. So this is what I call the equisingular approximation theorem. Indeed, this is possible. Although it's not possible with analytic singularity. So here the claim is not that the phi nu have analytic singularities. They are certainly smooth on the complement of an analytic set, but in general with non-analytic singularities along Z nu. But then if you allow this larger flexibility, then you can achieve that the ideal sheaf of H nu is equal to the multiple ideal sheaf of H, again with an arbitrary small loss in the positivity of the curvature. And then whatever I explained works. Okay, so that was the situation in the year 2001. But now, well, my PhD student Xiaojun Wu, who defended last December 2020, I asked him to work again on this, and he obtained a very substantial improvement of our initial result. So, in fact, if you look at the harmonicity, it turns out that the solution you construct here by division in the Lefschetz map turns out to be in the kernel of the 1-0 part of the connection here. So this del H is the 1-0 part of the Chern connection. Of course, it's a highly singular connection because you have arbitrary singularities on the weight, but you can still make sense of this in the sense of distributions. So you have a kernel. And now if you intersect this group with the kernel, then the surjective morphism becomes an isomorphism. So it's much better. It's much better. So you identify in the holomorphic sections, you identify precisely the subspace for which you have the isomorphism in the Lefschetz map. And even more, now, if you look at those sections, you can interpret them as actually parallel sections with respect to this very singular chain connection. But nevertheless, it can be shown, again, by an argument I used almost 20 years ago in a different context, that this gives rise to a holomorphic foliation of X. Simply, you look at the subsheaf of terms of tangent vectors that contract. So you have an n minus q form here. So you look at tangent vectors that contract your n minus q forms to 0. So you get the coherent subsheaf because you have a homomorphic section, maybe with singularities. And you can show, because of this parallel condition, that now you get an integrable subsheaf and therefore you get a foliation. So now somehow in this very, you don't have vanishing of the cohomology, but somehow now you understand very much why the cohomology is non-zero. So it comes precisely from certain holomorphic objects that are n minus q forms that give rise to holomorphic foliations of your variety. And this is true even in the Keller case. Certainly in the Keller case, you might get very transcendental foliations, but the hope is that this can be used to analyze now the behavior of line bundles that are only pseudo-effective, also in the projective situation, and possibly analyze what happens to the MMP in this general context. And the proof is quite easy, so I will terminate with this here. So in fact, you look, in the sense of distributions, you look at the integral of del h v h square. It turns out that this is convergent because you have, well, you are in the ideal sheaf, okay, because of the hypothesis of the ideal sheaf and because of the Guan and Zhou theorem. Okay, you write it as a pairing. Okay, you integrate by parts, so you commute the del h connection 1, 0. So by conjugate linearity, it becomes the del bar here. But now del bar v is 0 because v is holomorphic. So actually you have here, you recover the curvature. The integration by parts give you a minus sign, but now the curvature is positive. So you get something negative, but you have a square. So this is to be 0. And so we had completely overlooked this fact. But in fact, the Lefschetz theorem produces parallel sections, and therefore you get foliations. Okay, so that's the main idea. Of course, I've skipped quite a number of technical details here, but well, okay, I'm going to stop here and possibly answer questions afterwards. So let me stop here.
You jump here. Okay. Thank you very much, Jean-Pierre. Are there any questions, remarks, request of application, minimum model program?
Or we keep questions.
So maybe I look at the chat.
We have also the question and answer with Jean-Pierre.
Yes.
Maybe we can take I don't know, 5 minutes of break, and then we can make this.
There is the question session afterwards. So maybe you can think of the question, and then I will try to answer them if I can. Of course, don't ask me to solve the minimum program right now. I still don't know.
Okay.
Okay. Thank you.
Okay. So we